Hello everyone and welcome to this module on Introduction to Continuum Mechanics. So in this module we're going to explain or reintroduce the principal equations using their integral format or formulation. So far we discussed these five principal equations: conservation of mass, linear momentum, moment of momentum, energy equation, and entropy inequality. However, this last one, in entropy inequality, it's not an equation, it's an equality. All right, so far we selected an element, or it's better to just have it here. So we select an element and we assume that this element is in a continuum, and by this I mean, basically this particle or this element is surrounded by an infinite number of particles. Therefore, we have a continuum. So we isolated this one, we took it out, and then we developed our equations based on this element. This is basically the global, right down here. So we had the principal equations. So this is the local representation of the principal equations, or the differential formulation, which we also developed for, let's say, the reference configuration as well as the form configuration. So let's say that you basically select. Now we are going to basically look at these principal equations from another perspective. This time we're going to select a fixed part of the material. So we select a fixed part of the material like this, and then we integrate over the whole material. Therefore, we will have a kind of global principal equation, or we call this the integral formulation of the principal equations, and this can also be characterized in its reference as well as the form configuration. So you should also know that you can always move from the local to the global, and vice versa. So if you develop a kind of field equation or principal equation in a local formulation, you can always move towards the global formulation. And if you develop your equation based on the global scheme or formulation, you can get back to the local formulation. All right, so with this motivation, let's get to the first principal equation, which is the conservation of mass. So based on this principal equation, we have the rate of increase, let's say, of the mass in a fixed part of the material. So we select a fixed part of the material and we say the rate of the increase of the mass in this let's say, in this fixed part of the material is always 0. So this means that if you have, for example, uh, you have deformation, or or something like that, then dm, so maybe that is the change in the material is 0. So instead of this d, so we have the material derivative of the mass here, m. So since we are selecting a fixed part of the material, therefore we will have d of dm dt is equal to 0. And since we said that we will basically integrate over the whole domain, over the material, therefore we have to change this to, so we have d dt of dm is equal to 0. And this, let's say, this domain is on Vm, on the volume of the material. And this m basically refers to the material. So now you can see that the material derivative of this part of the material, this small dm, is equal to 0. And since we are discussing the global or the integral formulation, we integrate over the whole domain, which is Vm, or the volume of the material. Or d dt of, instead of dm, we write rho dv is equal to 0 over Vm. So this is the global representation. So now we are going to basically move from here to the differential format. All right. So here we have selected a part of the material. Here it's Vm. And let's say that this is a part of the, let's say, a fluid, for example, because this can be best described within the concept of fluid mechanics. And then you have a kind of the same volume here, but we call it VC, or control volume. So this is material volume. At an instant, this is moving basically. At an instant, these two, they coincide. So this becomes Vm. So Vm is equal to Vc. At this moment, we can take this material derivative inside the integral. And instead of Vm, we write Vc, or maybe it's better to write it Vm equal to Vc. So we will have d of dt integral of rho dv over Vm. This is basically changing to this d, so it becomes d dt. At that instant, Vm becomes Vc rho dv. We can take this material derivative inside the integral. So we replace this Vm with Vc, then we have d dt, the material derivative of rho dv is equal to, so we take the derivative. So this becomes the integral over Vc d rho, the material derivative of the first times the second one plus rho d dv dt. And this is basically equal to 0. So we also know from previous modules and also equation 3, 13, 14, we know that 1 over dv d dv dt is equal to the divergence. So we can replace this one. So it's the divergence of v, or partial derivative of vi respect to xi, and this is the velocity. Remember, this is not v, so this capital V is the volume. So based on this, we can write, so if we use, for example, 1, then we can write this as integral over vc. We have d rho dt dv plus then we have, so this is d dv dt, so we will have dv divergence of v, and we also have rho in here, so this becomes rho divergence v dv is equal to, so if I factor out dv, then I have d rho dt plus rho dv d capital V, which is the volume in here, and this is equal to 0. So for this equation to be available for every control volume that we select, we need this expression here inside the parentheses to be equal to 0 based on the principal lemma of calculus. So let's see what this principal lemma of calculus say. So based on what is given here from the book Theory and Analysis of Elastic Plates and Shells, second edition by J. and Reddy, says that fundamental lemma of calculus of derivatives. So based on this, we have for any integral function like g, the integral g dot n, let's say eta x dx from a to b is equal to 0, this holds true for any fundamental function eta x between a and b. So for this one, if it's gonna be true for any function eta x, then g should be equal to 0 in the range of a and b. So therefore, based on the principle lemma calculus of derivatives, we can write that d rho dt, the material derivative of rho dt plus rho dv, should be equal to 0 for any volume control that we take. Therefore, so let me just copy. Therefore, we have this expression in here. This is the derivative, the differential form. And remember, this is the differential form in deform configuration. So we can also write this in the partial differential, or maybe it's better to write this as the material derivative format. And then if you recall, we had d of rho is a scalar value. So the material derivative of d rho dt was equal to the partial derivative of p with respect to t plus v dot del rho. So basically, if we substitute this in this, so if we substitute 2, so from 2, we get partial derivative of p with respect to t plus v dot, del p plus rho divergence of v, and this is basically the divergence of rho v. So it's the rho divergence v plus v, this becomes the del p, del rho. So we can write this as the partial derivative of rho with respect to t plus divergence of rho v equal to 0. This is the partial derivative form, and it's again in deform configuration. So in order to write these two equations, either material derivative or this partial derivative in in reference configuration, so to convert, let's say 3 and 4, or to write 3 and 4 in reference configuration, we have to replace rho with rho 0 divided by j, because if you remember, rho 0 was rho Jacobian. And that's it. All right. So now let's get to the second principal equation, which is the linear momentum. But before that, the book actually put another topic forward, which is the divergence theorem. All right. So if you wanna mm, if you want to describe the divergence theorem in simple like words, we can say it's kind of theorem that within that you can use an integral, you can convert an integral on the volume to an integral on the surface and vice versa. So this is a very, very rough, let's say, very rough definition for the divergence theorem. So let's say that you have a domain, and suppose this is in 3D, so it's not 2D at all. And this has, this has VC, so it has a control volume, and then this has a normal N, and on the surface, so this is the surface, we have SC. So you have a volume, and this volume has a surface, so it's like a ball. So this ball is a sphere, so it has the volume of a sphere, but it also has a skein, or it has a surface. We call that SC. So if you have a vector or a first order tensor, so the integral of the divergence of that vector or first order tensor on the volume VC, it becomes equal to, so this is delta to V on VC dV. This is equal to, so this volume becomes the control surface, so it is SC. Then it becomes V dot N. V, the vector that you have, or the first order tensor that you have, dot normal to the surface, ds. Or it is equal to the partial derivative of vi with respect to xj. Let me just write it down here. Or the integral, we have divergence, so vi with respect to xj on vc dv is equal to, so it becomes it becomes, since this is divergence, so it is vj dot nj ds on sc. So if you have a tensor, then what happens? So if t is a tensor, you have the divergence of t dv over vc. This is equal to t n ds on sc. So basically, this partial derivative of tij with respect to xj dv on vc becomes equal to the integral of tij. Then we have nj. Look at this subscript in here as well as in here. So we have nj ds over sc. So using the divergence theorem, we had this equation here. We had this equation in here, which was 3. Sorry, it was 4. This one in here. So equation 4 we had just copy and paste it. VC, this is equal to 0. So if this is equal to 0, therefore we will have integral partial derivative of rho with respect to t dv on vc is equal to, then we take this to the right hand side, so it becomes minus of the divergence of rho v dv vc, and this divergence is basically del dot rho v. So since this is a vector field, it becomes minus rho v dot n ds on s c. So this means that the rate of increase in mass is equal to, yes, it is equal to the mass that enters the control surface. And why it enters? Because we have a minus sign in here. We already mentioned here in this in the supplied heat, we say that when a heat is basically entering our domain, so let's say that you have a door in here, so these which are entering from the boundary inside the element that you selected, we have a minus sign for that. So that's again here. So this shows that we have the mass that enters the control surface. So whatever, so if you have a material, part of the material, this is your part of the material, so the rate of increase in mass is equal to the mass that enters. So this enters and it goes out from the other side. Therefore, the conservation of mass says that this rate of increase in mass in a fixed part of the material is always zero. So whatever input you have, you will have that as the output. And that's all about the conservation of mass. Now let's get to the next topic, which is the principle of linear momentum. So based on this principle, so the force or the forces that you have, and here when I'm saying forces, I mean the both surface and body forces. Body forces acting on a fixed part of the material, fixed the material or material, this is equal to the rate of change linear momentum. So this means in mathematical format, so we have the surface forces, so we have T, they are on the surface, so we have SC plus the body forces, they are volumetric forces, and the book actually used B, which is forced by mass. So for this, we put a rho and dv in here on Vc is equal to the rate of the change of linear momentum. And linear momentum is mv, right? Sorry, mv. And since we have a fixed part of the material, then we have dmv, or rho dvv. And this is volume, this is velocity. Therefore, we will have rho small v dv. on Vm. So instead of T, I can write T capital N ds on SC plus the integral of rho b dv over Vc. This is equal to d dt integral of rho v dv Vm on Vm. So when our control volume, when our material, fixed part of the material coincides our control volume at that instance of time, so when Vm is equal to Vc, we can take this material derivative inside the integral. So we'll have d dt of rho v dv over Vm is equal to the integral over Vm. We take this inside d dt of rho v dv. And this is when rho v is equal to Vc. So this changed to Vc. So I can also write Vm equal to Vc. So if I expand this, then I have, again, Vc in here. So if I take rho and dv as one term and then small v as another term, I will have d of, let's say, let me write rho or d dt of rho dv v plus, write it this way, then we have rho d, or maybe dv dt rho dv, right? Then this one here is the conservation of mass, which is 0. Therefore, we only end up with this expression. So dv dt rho, and this is dv. So using the divergence theorem, because here we have SC and here we have VC, and here we have also VC. So we have to convert this SC into VC. So from surface, we have to go to the control volume. From this controlled surface, we have to go to the volume control volume. So using the divergence theorem, we can write the integral of the divergence of t, this one. So, sorry, this was Tn ds, Tn ds. So this is equal to, this becomes the divergence of t dv. Therefore, we can write this equation, we can rewrite this equation as divergence of t dv on Vc plus yet rho b dv on Vc is equal to this integral here. So we have rho dv dt dv Vc. Now we can take everything to the right hand side. So we'll have Vc, we have rho, and I factor out dv. So dt minus the divergence of t plus rho, minus rho b dv is equal to 0. And again, using the principal lemma of calculus, we have this equal to 0, so rho dv dt is equal to the divergence of t plus rho b. So, and this is in its material derivative, and it's in the 4 configuration. So Here you have to change rho and t to their corresponding values with their corresponding alternatives in the reference configuration in order to capture the this equation in the reference configuration. So next we have the principle of moment of momentum. So basically, based on this principle, we show that Tij is equal to Tji. So here, this principle of moment of momentum states that so the moment about a fixed point of all the forces, and again here I mean the surface and body forces. So the moment about a fixed point of all the forces of or on a fixed part, yes, on a fixed part of the material or of a fixed part of a material, this is equal to the rate of the change, the rate of change of moment of the rate of the change of the moment or rate of change of momentum about the same point. Same point. So here we have the moment. So the moment was, if you remember from a static, it was r cross f. So you had a force f, and you also had a vector r. So r cross f was the moment. So here, the moment about a fixed point of all the forces. So you have some surface forces. So if the vector is x, so we have x cross t ds on SC plus x cross, again, rho b dv on VC is equal to the derivative, it's equal to the material derivative or the rate of the change d dt of of the momentum about the same point. So we have x again cross, the momentum is rho v d capital V on Vm. So this one can be written as, so x cross, we have Tn ds plus, then on the Vc we have x cross rho b dv, which is equal to the d dt integral of x cross rho v dv v. So here we have SCVC and this one is Vm, so we have to change this Vm to Vc and also SC to Vc using the divergence theorem. So when Vm is equal to Vc, so we can write the dt of integral x cross rho v dv. So we can take this derivative d dt inside the integral. So then we'll have the integral of d dt x cross rho v dv on Vm equal to Vc. So if we do this, then we get, so we have the first derivative, so it is dx, sorry, this is the integral on VC of, let's say, dx dt cross rho v dv plus x cross d of rho v dv dt. So this one here, dx dt is v, and we also have this in here. So do we need to figure out? So we have the d of rho v d capital V dt. So I take rho and dv as one equation. So one, let's say, one variable. So we have d v dt rho dv plus v d rho dv dt. This is 0 due to conservation of mass. And again here, since rho is a scalar value, here we have v cross v. So v cross v means this expression whole is equal to 0, because a cross a is a squared, or let's say a sine theta, where sine here, where theta here is 0, therefore sine is 0. So finally, we get, where we see we have x cross, we only have this expression here, dv dt rho dv. We only have this expression in here. So here we have a vector, and here we have a vector. So here we also have a vector, and here we have a vector again. But let's write this in here. So just highlight it with another color. So I'm gonna grab this. Paste this in here. Maybe change the color of this one as well. And this one. All right. So now we have this. This is a vector and this is a vector, right? So I can write x cross tn. So if I write this in indicial notation, I will have, for example, xj cross tnk. So if you have a j cross b, a j e j cross, let's say, a b k e k, then you had a j b k, then you had j k. So we had I, j, and k, and then this became epsilon I. Sorry, this became k, j k I, j k I, and then yeah, then we had e I, right? So, and this was, this jki was, jki was equal to ijk, if you remember. So therefore, this can also be written as xj, or I can write it xjej cross ek, ej cross tn ek. So this became xj tnk And here we have epsilon I j k e I. This can be further broken into xj t k m n m epsilon I j k e I. So this basically gives us a vector tn k, because m here is a dummy index, and here for this to be applicable, this second one should be equal to m in here, so they should be both m and m. It's like the matrix product, something similar, analogous to that. So just keep this in here, so t and k. So therefore we get something like this, and I can take out this, so we have xj t km epsilon I j k e I, then we have nm. So then we have this integral on sc, so it became xj t km epsilon I j k e I nm. And using the divergence theorem, then this becomes vc, the divergence of this, or the partial derivative of xj t k m epsilon I j k with respect to. So this is going to give us, and this is ei, so this is going to be x, so we have j, we have k, this is I, and so this is going to be m because we have I in here. All right, so if we expand this, then we get ei, we put ei here so we don't lose the track, and we also have this ds in here, and this is dv. All right, so the partial derivative of xj respect to xm t, let me write bracket in here, so this becomes t km epsilon I j k plus, because we also have this ei outside, so let me just put it inside. So because I can write this ei in here, maybe it's better. So to factor everything right here, then we have dv plus, then we have the integral of xj partial derivative of t km respect to xm epsilon I j k e I dv plus the integral, and this is over vc, of course. We have vc. We also have xj t kn partial derivative of epsilon I j k with respect to xm ei dv plus the integral of xj over vc, of course, t kn epsilon I j k partial derivative of ei with respect to xm is equal to. So this is a constant value, is either 0 minus 1 plus 1, so this is 0, and this is also 0 because it is a constant value. So this one here, we already know from the first module that this is delta ij, or here jm it becomes. So, and this is equal to 1 when j is equal to m, otherwise it is 0. Therefore, here we have j equal to m. We have the integral over vc of t. Instead of m, I put j, t j epsilon I j k e I dv plus the integral. Then we have over vc xj partial derivative of t km with respect to xm epsilon I jk ei dv. So if I factor out ei and dv, I get ei on vc. So this is t kj epsilon I jk plus xj partial derivative of tkm with respect to xm epsilon I jk dv. Right, where this one here can be written as x cross divergence of t. Divergence of t, because we have epsilon I jk, and then we have partial derivative of tkm with respect to xm. So this is the divergent. This is divergence of t, tensor t. This is x. This is basically x cross divergence of t. So I can copy this in here and write this as, so this ei only goes to this one, sorry, because it is already included in this equation here, plus x cross divergence of t. And then we also have this in here, so maybe this is, so the last one was 4, I guess, so this is 5. So then we have x cross rho b over c rho b dv. This is equal to this. So I already wrote down this here, 5. So this is again 5. So we have over vc t kj epsilon I jk e I dv plus, then we have x cross, so we have the divergence of t plus, then we have, okay, this is x cross rho b, so we have rho b, yes, then we have, yes, dv is equal to d dt, and here we have vc, of course. So this is equal to integral over vc x cross rho v dv. Just move this down a bit. Right. And we already showed that this x cross rho v, where is it? It's equal to this one. So if I just get rid of this, so if I take everything to the right hand side, then I'm gonna have d I forgot this d dt, and let me check if I missed it here or not. So this is d dt, and we took this one, so it is d over dt, and so this is d over dt. All right. d over dt of integral for VC x cross, so we have dv dt rho minus we have divergence of t minus rho b dv, and then we have this minus the integral of ei or tkj epsilon I j k e I dv over vc is equal to 0. So according to the linear momentum, the principle of linear momentum, this is equal to 0. Therefore, minus of the integral t kj epsilon I j k e I dv over vc is equal to 0. So let's find out these values in here. So we have k and j as the DOM index indices and I as the free index. Therefore, we sum over the, let's say, the DOM index. So, and this has three, let's say, three equations, because we have I and I can occupy 1, 2, and 3. All right, so we're gonna have epsilon I, then j is 1, so I k t, so we have k1 plus epsilon I2k tk2 plus epsilon I3k tk3. So then this is equal to epsilon I, then k is 1, so 1 1 t, k is 1 1 1 plus I2 1 1 2 plus I3 1 t 1 3 plus, then we have ks2 1 2 t2 1 plus I, oh sorry, yes, this is 2 2 t 2 2 plus epsilon I 3 2 t 2 3 plus epsilon this is 1 2. So this is I 1 and k is 3 t 3 1 plus epsilon I 2 3 t 3 2 plus epsilon I 3 3 t 3 3. So since we have here t, we have epsilon I 3 3, so whatever I we have in here, so this becomes 0. This is also the same. This is epsilon. This is 0, and this is also 0. So if I, for example, say that here I is 1, so it becomes 0, 2, this again goes 0. So only here I can put 3, 2, 1, t1, 2 plus. Here we have epsilon, so only I can take 2, 2, 3, 1, t1, 3 plus. So I can take only 3, 3 1 2 3 2 1 plus. Here I can take 1 epsilon 1 3 2 t 2 3 plus. Then we have I here can only take 2 2 1 3 3 3 1 plus. I here can take 1 1 2 1 2 3 3 2. Then we know that we have epsilon 1 2 3 equal to 3 2 1 equal to 3 1 2. This is equal to 1, right? So 2 3 1 and 3 1 2, and then we have epsilon. So we had 1 2 3, so 1 3 2 1 3 2 3 2 1 3 2 1 and 1 3 2. These are all equal to -1. So 3 2 1 epsilon 3 2 1 is -1. 2, 3, 1 is 1. 3, 1, 2 is 1. Epsilon 1, 3, 2 is -1. 2, 1, 3, 2, 2, 1, 3, 2. So I made a mistake in here. Or 2. Okay, 1, 2, 3, 2, 3, 1, and 3, 1, 2. 1, 3, 2, 3, 2, 1, and this is 2, 1, 3. So 2, 1, 3 is -1, and 1, 2, 3 is 1. And this is basically equal to 0 here. Therefore, from here, if we sum similar terms, so we have minus t21 plus t21 equal to 0, then we have t13 minus 331 is 0, and then we have 3 minus 3 2 t23 plus t32 is equal to 0. So this means that t12 t, and this is supposed to be, I made it, yes, this is 1 2. So t12 is equal to t21, t13 is equal to 31, and t23 is equal to t32. All right, next we have the conservation of energy or energy equation. So based on this principal equation, we have the rate of increase. So the rate of increase of the kinetic energy and internal. So let me just write it, kinetic energy and internal energy in a fixed part of a material. This is equal to the sum of work done by the external forces, and this is sum of the rate of the sum of the rate it doesn't, let me just, so it's the sum of the rate of the work or the power done by the external forces. And again here, by forces I mean we have the surface forces plus the let's say the body forces. Forces. So, and the rate of heat inflow and the heat generated inside, or the heat supplied inside or throughout. So in mathematical format, we have the material derivative of the summation of the kinetic energy plus u, or the internal energy, dv over vm, is equal to, so we have here the surface forces, we have the t, and here since we have the rate, so we have dx over dt, so this is v, so this is t dot v, and here we have a number, so it's a zero scalar tensor, zero order tensor or a scalar, so we will have t dot v, and it is over s on the surface plus the work done by the rate of the work done by the body forces. We have rho b v dv, and here we have b dot v on vc plus the rate, so it becomes minus because it is entering from the boundary. So q dot v ds, and it's from the boundaries, so it is s plus the integral of rho qs. It is generated inside, so it is del v, so dv, and here we have vc. So this one here, we can rewrite this as, this can be written as rho v squared divided by 2, and this can be written as, we know that small u is u divided by mass, so u can be written as mu, or this m, it can also be written as rho dv. So we can rewrite this equation as d dt of the integral, where vm rho v squared half plus rho u dv. This is equal to the integral of this in here. So let me just copy and paste this here. All right. So when Vm coincides with Vc, we can take this derivative inside the integral, so we will have the integral of the dt over Vc, because Vm is now Vc, the same as them. So rho v squared half plus rho u dv. This is equal to the material derivative of, so I have rho both in here, so I can write this as v squared half plus rho plus u rho dv over vc. So I also have sc here in here, so I have to convert them using the divergence theorem to vc, to the control volume. So I have sc t dot v ds on sc, so I have tn dot v ds, which is equal to, so I can write this as n dot t transpose v ds, so I can write this as n t transpose, so this becomes n dot t transpose. This is equal to sc, so since this is dot, I can write this as t transpose v dot n ds, and this t transpose v is basically, so if I take the derivative, the divergence of t transpose v, we can write this as the partial derivative of t transpose I j vj respect to xi, because here we have finally a vector, and divergence actually reduces one order of the tensor that we have, so we finally get a scalar value. So that's why here we have two i's and two j's. So we take the partial derivative of t ji, so this becomes tji vj, because this is transpose with respect to xi. It's equal to the partial derivative of ji with respect to xi vj, so we call this 6, plus tji partial derivative of vj with respect to xi. So if we swap I and j in the first one, so here we swap I and j. So what we get is the partial derivative of tij. So tij again is equal, so let me write it completely. So we have xj vi plus tji partial derivative of vj xi. So we know that here tij is equal to tji because the Cauchy stress tensor is symmetric. So we can write this as partial derivative of tij. So we can write this as t transpose. So now we have the divergence of v plus, here we have this t divergence of, t v v plus, I put a dot in here because we have two i's and two j's, so it's a scalar, tji partial derivative of vj xi. And you have to be careful here. That's 6, which is, let me just copy and paste it. Or maybe I can move all this down. So perfect. So this is equal to, this is VC, this is the divergence of T transpose V dV, right? So we have the divergence of T transpose V in here, and we found it that it is equal to this one. So we want to know what is this one. So let me change the color. We copy and paste this in here. So this is equal to, I can write this as half of tji partial derivative of vj, and I think that I made a mistake in here. So yes, we're not going to swap I and j in here. So finally, we end up with this tji xi. This is the divergence of t. Sorry about that. So we have to push this bit up. So we have the divergence, this is the divergence of t dot v plus tij, this in here. And for this one, we can write this from this stress power module. We know that we can write this as partial derivative of vj with respect to xi. Plus, again, half of this value. So tji partial derivative of vj with respect to xi. So in the first one, we swap I and j. So we get half of, let me just write down here. So we get half of t ij, partial derivative of vi with respect to xj, plus half of t. So ji is itself, partial derivative of vj with respect to xi. So since we know that tij is equal to tji, we can write this as tij. Then we have half of, this is partial derivative of vi with respect to xj plus partial derivative of vj with respect to xi. This is basically t times half of del v plus del v transpose, which is the symmetric part of the velocity gradient, which is td. So this is equal to the trace of td. So this is the trace of td. Or we can write this as t transpose del v, or trace of td. All right. So the integral of now t dot v is equal to this value, and it is equal to, so t dot v dv over sc is equal to, so first we have the divergence of t dot v plus this trace, the trace of t transpose, so t transpose del v, or t d del v. So we also have q dot n ds over sc. So using the divergence theorem, we can write this as, the divergence of q over vc dv. So then we have, so we already converted this one, and these are both on vc. So I can write this whole again. This is equal to, so I can take out rho as well. So rho dv, this is u, and here we have v squared divided by 2. So it is first this expression here. So on vc, you have the divergence of t dot v plus the trace of t transpose del v, plus we have, let's say, so this is, let's call this 6. So we have this, copy and paste, so I have all the same terms in here. So then we have rho b dot v, then we have minus divergence of q, plus then we have rho qs dv. Awesome. So if we take this divergence with this, so we have vc, so this divergence of t plus rho b dot v, plus then we have this trace of t transpose del v minus the divergence of q plus rho qs dv. So this is the divergence of t plus rho b. So we also know that the divergence of t plus rho b change the color of this. So this can be written as rho A, or we can write this as rho dv dt dot v. So, sorry, rho dv dt. And since we have dot v in here, so maybe I can write this dot v in here. So we have this dot v and then dot v in here. So we have to see what is this one, this expression in here. We can prove that this equation here is equal to half of rho dv squared dt. So basically, if we have half of rho dv squared dt, this is equal to half of rho. So if I take the derivative, so it becomes 2v dv dt. So this 2 cancels out with this one. So it becomes rho dv dt dot v. So I can change this color in here. So this is provided in here. So therefore, we have this expression in here. So we have rho dv squared, if I'm not mistaken, let me check, dt over vc, v squared half plus u dv is equal to, so then we have, let's say, this expression, half of rho dv squared 2 divided by 2, and it's an integral. So it is vc plus, then we have, so we have this one, then we have the trace of t transpose del v, then we have minus divergence of q, then plus rho qs, and whole dv. So this expression here, so if we expand this, so rho dv squared, and this is half, right? So I can take half in here. So this is rho dv squared dt dv plus, so we have rho du dt dv vc vc. So we can cancel out this one with this one. So we finally get rho du dt. I take all to one side. So this is rho du dt minus, I have the trace t transpose del v plus divergence of q minus rho qs dv on vc is equal to 0. So based on the lemma, the principal lemma calculus, then rho du dt is equal to the trace of t transpose del v minus the divergence of q plus rho qs. That's it. All right, so the next and the last field equation, or it's better to say inequality, is entropy inequality. So based on entropy inequality, we say that the rate of increase of entropy in a fixed part of the material it is at least equal or bigger than the entropy caused by the heat or the influx heat on the boundary plus the entropy caused by heat generated inside or throughout the volume. So in mathematical format, we have dt of entropy. So we define entropy as entropy divided by mass, right? So it is entropy, so it is rho eta dv over Vm is greater or equal to the, so it's influx heat or the heat on the boundary. So we have Q minus Q theta dot n ds, and it's from the boundary. We have SC plus, then we have rho QS divided by theta dV Vc. So here you have to be careful in all the equations that we developed in this module. Here, this is your control volume or surface. SC is here and Vc is inside this. So you select Vm and this Vm is moving up until it comes and it coincides with this control surface or control volume that we found, that we basically defined. So at that moment, this Vm becomes Vc. So that's why we write this in VCSC and this one is in Vm. You have to be careful about this. So now when Vm is equal to Vc, then what we have, we can take this derivative inside the integral. So we have the derivative, the material derivative of rho eta dv is equal to the integral on integral Vc. So d eta, I take eta as one and rho dv as another, dt rho dv plus eta d rho dv dt. So due to the conservation of mass, this is equal to 0. Right this way. So we only have this one in here, so it becomes the d eta dt rho dv. Vc is greater or equal to minus. So this one is SC. So we have Q divided by theta, that's N. So using divergence theorem, we can write this as the divergence of Q over theta. This is Vc dv plus the integral of rho Qs theta dv on Vc. So if I take everything to one side and again using another kind of let's say principal lemma of calculus, similar to this one in here, but this one, instead of being equal to 0, it is greater or equal to 0. This also holds true. I mean, the other one, the other fundamental lemma of calculus, not this one specifically, because this one is for the equalities, but this one is for inequalities. We also have something like that for the inequalities. And again, based on that, we can write in here that rho d eta, so if I take everything to one side, rho d eta dt plus the divergence of q over theta minus rho qs theta dv is greater or equal to 0. Therefore, this is equal to 0. So we have rho, this is greater or equal to 0. So we have d eta dt plus the divergence of q theta minus rho qs divided by theta is greater or equal to 0. Therefore, we have rho d eta dt is greater or equal to minus the divergence of q over theta plus rho qs theta. And so basically this module now ends, the third module or chapter 4 of the book. So up until now we actually derived all the equations, the principal equations in their material as well as integral formulation. And now in the next module, which is our last module, we will derive the principal equations using the Reynolds transport theorem. And this is basically and we basically use this use these equations in Reynolds transport theorem to solve some problems, but overall we will not basically put anything new. We don't put anything new forward, so it's all about just the repetition, the principal equations, and deriving them and looking at them from another perspective.